Imagine for a moment that you are standing perfectly still. You feel stationary, grounded, certain of your place in the universe. But the truth is far more unsettling. Right now, as you listen to these words, you are hurtling through space at over 1.3 million miles per hour. Not just you, but your house, your city, your entire planet, the sun, and every star you can see in the night sky. Our entire galaxy, the Milky Way with its 100 billion stars, is being dragged through the cosmos by something we cannot see. Something so massive and so distant that it defies our everyday understanding of reality. We call it the Great Attractor, and its existence forces us to confront a terrifying possibility. That even in the vast emptiness of space, we are not in control of our destiny. Close your eyes and picture the Milky Way. That beautiful spiral of stars stretching across the night sky. That river of light that has inspired poets and dreamers for millennia. Now zoom out. Keep zooming. Past our neighboring galaxies, past the local group, past the Virgo supercluster. Zoom out until our entire cosmic neighborhood becomes just a small collection of lights in an even greater darkness. From this perspective, something extraordinary becomes visible. Thousands of galaxies, including our own, are streaming in the same direction like leaves caught in an invisible current. They are falling, accelerating, being pulled by something hidden in the depths of space. This is not a slow drift. This is a cosmic stampede, a gravitational avalanche happening on a scale that makes our entire existence seem like a brief flicker in an incomprehensibly vast dance. The question that should be forming in your mind right now is this: what could possibly be powerful enough to pull billions upon billions of stars across distances so vast that light itself takes hundreds of millions of years to cross them? What lurks out there in the darkness, exerting its invisible grip on everything we know? And perhaps more disturbingly, where is it taking us? The story of the Great Attractor begins not with what we could see, but with what we could not explain. In the late 1970s, astronomers were conducting routine observations of galaxy movements, expecting to find what scientists call the Hubble flow, the general expansion of the universe that carries galaxies away from each other as space itself stretches. They found something else entirely. Galaxies were not moving the way they should. There were deviations, peculiar velocities that suggested something massive was interfering with the expected cosmic order. Imagine you are watching leaves floating down a stream, and suddenly several of them veer sharply to the left, as if caught by an underwater current you cannot see. That is what astronomers were witnessing on a galactic scale. In 1986, a team of astronomers known as the Seven Samurai, comprising Sandra Faber, David Burstein, Roger Davies, Donald Lindenbell, Roberto Turlovich, and Gary Wegner, published findings that would shake our understanding of cosmic structure. They had measured the velocities of elliptical galaxies and discovered that our local group of galaxies, along with thousands of others in our cosmic neighborhood, were moving toward a specific region of space at approximately 600 kilometers per second, or about 1.3 million miles per hour, on top of the universe's general expansion. This was not random motion. This was directed, purposeful, as if something out there was calling to us. They named this mysterious gravitational anomaly the Great Attractor. And with that name came a flood of questions that we are still attempting to answer decades later. Ask yourself this: if something that powerful exists, what does it look like? How big is it? And most importantly, what happens when we reach it? The location of the Great Attractor was determined to be approximately 220 million light-years away from Earth, in the direction of the constellations Triangulum Australe, Norma, and Circinus. To put that distance in perspective, if you could travel at the speed of light, moving at 186,000 miles per second, it would take you 220 million years to reach it. The light we see from that region today left when the first dinosaurs were just beginning to walk the Earth. Yet despite this unimaginable distance, its gravitational influence reaches across the void to pull at our galaxy with invisible fingers. But here is where the story takes a darker turn, where cosmic mystery meets cosmic frustration. The Great Attractor lies in what astronomers call the zone of avoidance. Picture the Milky Way galaxy not as we see it in beautiful photographs taken from space, but from our perspective trapped within it, embedded in one of its spiral arms. We are looking at the universe through the disk of our own galaxy. In most directions, we can peer out between the stars into deep space, observing distant galaxies and cosmic structures billions of light years away. But in certain directions, particularly toward the galactic center, we are looking through the thickest part of the galactic disk. There, countless stars, vast clouds of dust, and enormous concentrations of gas block our view like fog blocks a driver on a dark highway. The Great Attractor lies directly behind this cosmic fog bank. It is hidden from us, concealed behind billions of stars and light years of dust. Visible light cannot penetrate this barrier. The very thing that is dragging us across the universe is invisible to our most powerful optical telescopes. It is as if nature is playing a cosmic joke, placing the answer to one of our most profound questions directly behind the one curtain we cannot pull aside. Think about that for a moment. Something massive enough to influence the motion of millions of galaxies is hidden in the one place we cannot easily observe. Does that seem like coincidence to you? Or does it suggest something more unsettling about our place in the cosmos? For years, the Great Attractor remained more concept than reality, more mathematical prediction than observed phenomenon. Scientists knew something was there because of its effects, the way you know wind exists not by seeing it but by watching trees bend. They calculated its mass to be tens of thousands of times greater than our Milky Way galaxy. They tracked its influence across millions of light years. But they could not see it, could not photograph it, could not definitively say what it was. Then technology advanced. Astronomers developed tools that could peer through the zone of avoidance using wavelengths of light that dust cannot block. Radio waves, infrared radiation, and X-rays became our new eyes, allowing us to glimpse what had been hidden. What they found was both an answer and a deeper mystery. Behind the zone of avoidance, in the direction of the Great Attractor, lies an enormous concentration of galaxies. Not just a few dozen or a few hundred, but thousands of galaxies clustered together in a structure called the Norma Cluster. This cluster is part of an even larger supercluster of galaxies, a cosmic metropolis of unimaginable scale. Here, gravity has gathered vast amounts of matter into a relatively small region of space. The combined mass of all these galaxies, their stars, their planets, their dark matter halos, creates a gravitational well so deep that it warps the fabric of space-time itself, bending the paths of nearby galaxies like a bowling ball placed on a stretched rubber sheet. But even as observations revealed the Norma Cluster and the structures around the Great Attractor, something did not add up. The mass that astronomers could observe, even accounting for dark matter, was not quite enough to explain the powerful attraction being measured. The motion of our galaxy and our neighbors suggested something even more massive than what could be seen, even with our new tools. Was there more hidden behind the dust, enormous structures not yet detected? Or was something else at play, some force or phenomenon we had not yet considered? This is where the story deepens, where we must zoom out once again to see an even larger picture. In 1987, just a year after the Great Attractor was announced, astronomer R. Brent Tully discovered something that would add another layer to this cosmic puzzle. Beyond the Great Attractor, at a distance of approximately 650 million light-years, lies an even larger concentration of mass. This structure, named the Shapley Supercluster after the astronomer Harlow Shapley, contains more than 8,000 galaxies, making it the largest concentration of galaxies in our nearby universe. Imagine standing in a valley, feeling a strong wind at your back pushing you forward. You assume the wind originates from directly behind you, but then you realize there is a massive storm system far beyond, creating an even stronger pull. That is the situation with the Great Attractor and the Shapley Supercluster. Our galaxy is caught between influences, being pulled by the Great Attractor, which is itself being influenced by the even more massive Shapley Supercluster beyond. We are caught in a cascade of gravitational attraction, falling toward something that is falling toward something else. Think about the implications of this for a moment. The universe is not static. It is not a peaceful arrangement of galaxies floating serenely through space. It is a dynamic, churning sea of matter, with vast currents carrying entire clusters of galaxies across cosmic distances. We are adrift in these currents, our motion determined by structures so large that our entire galaxy is just a speck caught in their flow. How does that make you feel? Small? Insignificant? Or perhaps part of something grander than you ever imagined? The detection and study of these cosmic flows revealed something profound about the structure of the universe. Matter is not distributed evenly. Instead, it forms a cosmic web, with vast filaments of galaxies stretching across billions of light-years, surrounding enormous voids where almost nothing exists. The Great Attractor sits at a junction point in this web, where multiple filaments meet. Galaxies flow along these filaments like water flowing through the branches of a river system, all being drawn toward the deeper gravitational wells. But the mysteries do not end there. In 2008, a team of scientists led by Alexander Kashlinsky announced a discovery that sent shockwaves through the astronomical community. By studying the cosmic microwave background radiation, the afterglow of the Big Bang itself, they found evidence of something they called dark flow. Clusters of galaxies, including those being drawn toward the Great Attractor, appear to be moving with an additional velocity, a coherent motion toward a specific region of space far beyond our cosmic horizon. This motion could not be explained by any known structures in the observable universe. The implications were staggering. Dark flow suggested that something beyond the edge of the observable universe, something we can never see because light from it has not had time to reach us in the age of the universe, was exerting a gravitational influence on our cosmic neighborhood. Or perhaps it suggested something even stranger, that the Big Bang was not perfectly uniform, that there were asymmetries in the very fabric of the early universe that created currents and flows persisting to this day. Some scientists even speculated about more exotic explanations. Other universes in a cosmic multiverse, structures beyond our space-time, physics we have not yet discovered. It is important to note here that dark flow remains controversial. Subsequent studies have both supported and challenged the original findings. Some astronomers argue that the signal is real and represents a profound mystery we have yet to solve. Others suggest it may be an artifact of how we process the data, a ghost in the machine rather than a real phenomenon. This is how science works, through challenge and verification, argument and evidence. The debate continues, and the truth remains uncertain. But let us return to what we do know with confidence. The Great Attractor is real. The motion it creates is measurable. The vast concentrations of galaxies in that region of space have been mapped and cataloged. We can now create three-dimensional maps showing the structure of the cosmic web in our cosmic neighborhood, revealing the Great Attractor not as a single object, but as a region, a concentration point in the vast tapestry of cosmic structure. Modern observations using facilities like the Parkes Radio Telescope in Australia have penetrated the zone of avoidance, cataloging thousands of galaxies that were previously hidden from view. These surveys revealed the full extent of the structures in that region, showing massive clusters and superclusters aligned in a vast wall of galaxies. The Great Attractor is not alone, but is part of an even larger structure called the Laniakea Supercluster, a name meaning immeasurable heaven in Hawaiian. Laniakea is our cosmic home on the largest scales we can currently map. It contains approximately 100,000 galaxies spread across 520 million light-years. All of these galaxies are gravitationally bound, their motions correlated, flowing along common paths within the supercluster's gravitational influence. The Great Attractor marks a central region within Laniakea, though not its exact center. We are learning that Laniakea itself is being pulled toward an even larger concentration called the Shapley concentration, which lies at the edge of or just beyond Laniakea's boundary. Take a moment to consider the scale of what we are discussing. You exist on a planet 8,000 miles in diameter. That planet orbits a star. That star is one of hundreds of billions in a galaxy 100,000 light-years across. That galaxy is part of a supercluster 520 million light-years across. And that supercluster is being influenced by structures even larger still. The scales are so vast that our minds struggle to grasp them. 1,000,000 seconds is 11.5 days. 1 billion seconds is almost 32 years. 1 trillion seconds is 32,000 years. These structures contain trillions upon trillions of stars, more stars than all the grains of sand on all the beaches on Earth, all bound together by gravity and flowing through space in a coordinated cosmic dance. Yet despite all we have learned, fundamental questions remain. What is the ultimate fate of our journey toward the Great Attractor? Will we eventually arrive there, our galaxy merging with others in that region to form an even larger gravitational concentration? The answer is more complex than you might expect. You see, the universe is expanding. This expansion, driven by dark energy, is causing distant regions of space to recede from each other at accelerating rates. On local scales, within superclusters, gravity is strong enough to overcome this expansion, binding galaxies together. But on larger scales, expansion wins. The Shapley supercluster, despite its enormous mass and gravitational pull, is being carried away from us by cosmic expansion even as we are being pulled toward it. We are in a cosmic tug-of-war between attraction and expansion, falling towards something that is receding from us. Current models suggest that we will never actually reach the Great Attractor or the Shapley supercluster beyond it. The expansion of space will eventually overcome gravity on these scales, and these structures will slip beyond our cosmic horizon, receding faster than light can travel, disappearing from view forever. In the distant future, trillions of years from now, the observable universe will be a much smaller, lonelier place. The galaxies in our local group, those close enough to be truly gravitationally bound, will merge into a single enormous elliptical galaxy. But everything else, all the distant galaxies we can see today, will have been carried away by expansion, their light redshifted into invisibility. This leads to a haunting realization. We live in a special time, perhaps the only era in cosmic history when intelligent beings can observe and deduce the true nature of the universe. Civilizations arising in the far future, after all distant galaxies have disappeared beyond the horizon, will look out and see only their own merged galaxy in an endless void. They will have no way to discover the Big Bang, no way to detect cosmic expansion, no way to know about dark energy or the vast cosmic web of structure. The evidence will have vanished. They will look at a very different universe than we do, and they will reach very different conclusions about cosmic history and structure. Does this possibility disturb you? That the universe is hiding evidence of its own nature, that we happen to exist in a brief window when the full picture is visible. Some scientists find this realization humbling and profound. It suggests that we should make the most of our observations now, that we have a cosmic duty to record and understand what we can while the evidence still exists. Others find it unsettling, wondering what evidence might already have vanished, what aspects of the early universe we can no longer observe because those signals have been lost to time and expansion. But let us pull back from the far future and return to the present and near future. What can studying the Great Attractor and our motion through space tell us about the universe today? What mysteries might it help us solve? One of the most profound questions in modern cosmology concerns the nature of dark matter and dark energy. Everything we can see, all the stars and gas and dust and planets, all the ordinary matter made of atoms, accounts for less than 5% of the total energy content of the universe. Another 27% is dark matter, invisible matter that does not emit, absorb, or reflect light but makes its presence known through gravitational effects. The remaining 68% is dark energy, the mysterious force driving the accelerating expansion of the universe. The Great Attractor and structures like it are dominated by dark matter. The visible galaxies are merely tracers, flags marking the locations of much larger dark matter halos. By studying how galaxies move within and around the Great Attractor, scientists can map the distribution of dark matter, testing our theories about its nature. If dark matter behaves differently than predicted, if its distribution does not match our models, it might give us clues about what dark matter actually is. Is it composed of unknown subatomic particles? Is it a sign that our theory of gravity needs modification? The motions of galaxies toward the Great Attractor provide a laboratory for testing these ideas on the largest possible scales. Similarly, the balance between gravitational attraction pulling us toward the Great Attractor and cosmic expansion pulling distant structures away tells us about dark energy. By measuring these motions precisely, by mapping how structure has formed and evolved over cosmic time, we constrain the properties of dark energy. Is it constant throughout space and time, or does it vary? Is it truly a property of empty space itself, as Einstein's cosmological constant suggests, or is it something more exotic, a new field or force we have not yet characterized? These are not abstract academic questions. Understanding dark matter and dark energy is essential to understanding the ultimate fate of the universe. Will expansion continue forever, eventually tearing apart even atoms in a big rip? Will it slow to a halt, allowing gravity to pull everything back together in a big crunch? Or will it continue at an accelerating pace, leading to a cold, dark, infinitely diluted big freeze? The Great Attractor, despite being a local phenomenon in cosmic terms, provides essential data for addressing these profound questions about cosmic destiny. Now consider another mystery, one that touches on the very origins of structure in the universe. In the moments after the Big Bang, the universe was nearly perfectly smooth, with only tiny quantum fluctuations creating slight variations in density from place to place. Over time, gravity amplified these small variations. Slightly denser regions attracted more matter, becoming denser still, while less dense regions lost matter, becoming voids. Over billions of years, this process created the cosmic web of structure we see today. But here is the puzzle. The structures we observe, like the Great Attractor and the Shapley supercluster, are among the largest gravitationally bound objects that have had time to form in the age of the universe. They are pushing at the limits of what our current models predict should exist. Some scientists argue that structures this large should not have had enough time to fully form and virialize, to settle into gravitational equilibrium, since the Big Bang. Their existence might be telling us something about the initial conditions of the universe, about those quantum fluctuations in the first moments after creation. Were the initial fluctuations slightly larger than we think? Was the early universe slightly different than our standard models suggest? Or are these structures not quite as viralized as they appear, still in the process of forming and settling? Observations of the Great Attractor and similar structures provide critical tests of our cosmological models, challenging our understanding of cosmic history. Let me paint you a picture of what the region around the Great Attractor might look like if you could see it from a cosmic perspective, if your eyes could perceive dark matter and gravitational fields. Imagine vast filaments glowing with the light of billions of galaxies, streaming through space like luminous highways. Where these filaments intersect, great knots of brightness mark the locations of galaxy clusters. The Great Attractor would appear as a particularly bright nexus, a shining web junction where multiple filaments converge. Around and through everything, invisible to ordinary light but visible in your imagination, would be the dark matter, a ghostly scaffolding of mass providing the gravitational framework that holds it all together. Galaxies would be flowing along the filaments like cars on a highway, their paths curved by gravity, all heading toward the brighter regions where mass concentrates. You would see our Milky Way, a modest spiral galaxy among billions, following its ordained path, caught in currents that have existed for eons, heading toward a rendezvous it will never complete due to cosmic expansion. The scale would be breathtaking, the motions majestic yet inexorable. You would witness a universe that is anything but static, a cosmos alive with movement and structure on the grandest possible scales. But the view would also be haunting. Between the bright filaments would be the voids, enormous regions of space hundreds of millions of light-years across where almost nothing exists. These voids make up most of the volume of the universe. In a very real sense, we live in the cosmic equivalent of an archipelago, islands of matter in a vast ocean of emptiness. The voids are not completely empty. They contain some stray galaxies and wisps of gas, but their density is far below the cosmic average. They are expanding faster than the average expansion rate, growing larger and emptier as cosmic evolution proceeds. This cosmic web structure, with its filaments, clusters, and voids, emerged from those tiny quantum fluctuations in the infant universe. Think about that. The position of our galaxy, the existence of the Great Attractor, the entire large-scale structure of the observable universe was determined by quantum randomness in the first fraction of a second after the Big Bang. We live within a pattern created by physics operating at the smallest possible scales, amplified by gravity over billions of years to create structures spanning hundreds of millions of light years. The smallest and largest phenomena in physics are intimately connected, cause and effect spanning 60 orders of magnitude in scale. Now I want to explore a question you might be asking yourself. Could the Great Attractor pose any danger to us? Should we be concerned that we are being pulled toward this massive concentration of galaxies? The short answer is no. Not in any time frame that concerns human civilization or even the long-term future of life on Earth. Remember, the Great Attractor is 220 million light-years away, and we are moving toward it at a relative velocity of about 600 kilometers per second. At that rate, it would take approximately 100 billion years to reach it, far longer than the current age of the universe. And as we discussed, cosmic expansion will likely prevent us from ever actually getting there. But suppose, hypothetically, that cosmic expansion did not exist or that some unknown physics allowed us to complete the journey. What would happen if the Milky Way merged with the structures in the Great Attractor region? Galaxy mergers are actually quite common in cosmic history. Our own Milky Way is in the process of merging with several smaller satellite galaxies right now, and is destined to collide with the Andromeda Galaxy in approximately 4.5 billion years. When galaxies collide, despite the violence the name suggests, the event is actually quite gentle for individual star systems. Galaxies are mostly empty space. The distances between stars are so vast that the probability of any two stars actually colliding during a galactic merger is essentially zero. Instead, the stars pass by each other, their paths perturbed by the changing gravitational field, but direct collisions are extraordinarily rare. The overall structure of the galaxies is disrupted, spiral patterns are erased, stars are flung into new orbits, and the merged galaxy eventually settles into a new configuration, usually an elliptical galaxy. For any planets orbiting stars in the merging galaxies, the event would unfold over hundreds of millions of years, far too slowly to be perceived directly. The night sky would gradually change as the other galaxy loomed larger and new stars filled the heavens, but day-to-day life on such a planet would be unaffected. There would be no catastrophic moment of impact, no cosmic explosion, just a slow gravitational dance resulting in a new cosmic configuration. However, there would be one significant change for any civilizations existing during such a merger. The close passage of billions of stars would gravitationally perturb the clouds of comets surrounding each star system. These perturbations could send comets plunging into the inner regions of solar systems, potentially increasing the rate of asteroid and comet impacts on planets. For Earth specifically, such an increase might spell doom for whatever species inhabited it at the time, just as an asteroid impact likely ended the reign of the dinosaurs 66 million years ago. But again, we are talking about events billions of years in the future, long after the Sun has exhausted its hydrogen fuel and begun its evolution into a red giant, rendering Earth uninhabitable anyway. The real significance of the Great Attractor is not any physical danger it might pose, but what it reveals about the universe we inhabit. It is a reminder of the vast scales and forces at play in the cosmos, of how much we have yet to understand, and of how our perspective on the universe has evolved. Consider the journey of human understanding. For most of history, we thought Earth was the center of everything, with the sun, moon, planets, and stars all revolving around us. Copernicus and Galileo showed us that Earth orbits the sun. Later astronomers revealed that the sun is just one star among billions in the Milky Way galaxy, and that the Milky Way itself is just one galaxy among billions in the observable universe. Each step was a lesson in cosmic humility, a realization that we are less central, less special than we thought. The discovery of the Great Attractor is part of this ongoing lesson. Not only are we not the center of the universe, but we are not even in control of our cosmic trajectory. Our entire galaxy is caught in gravitational currents far stronger than anything we can influence, being swept along paths determined by structures so large they make our galaxy seem insignificant. We are passengers on a cosmic journey we did not choose, heading toward a destination we will never reach. Yet there is something empowering in this knowledge as well. Despite our small size and our brief existence, we tiny beings on this pale blue have managed to deduce the existence of the Great Attractor. We have measured its influence, mapped the structures around it, and placed ourselves within the vast cosmic web. We have developed tools and theories that allow us to comprehend scales of space and time far beyond our direct experience. We have, in a sense, transcended our limitations through the power of observation and reason. This is one of the great achievements of human civilization. The ability to ask questions about the universe and to find answers. Where are we? Where are we going? What forces shape our cosmic destiny? These are not questions with practical answers that will help you in your daily life, but they are questions that speak to something deep in the human spirit, a desire to understand our place in the grand scheme of existence. The Great Attractor also raises philosophical questions about fate and free will on a cosmic scale. If our galaxy's path through space is determined by gravitational forces that have existed since the early universe, shaped by quantum fluctuations in the first moments after the Big Bang, then in what sense is our trajectory chosen or random? The initial conditions were random, quantum in nature, truly indeterminate. But once said, the evolution was deterministic, gravity inexorably pulling matter along predetermined paths. We are the product of both chance and necessity, randomness and law. Does this cosmic determinism extend to smaller scales? Are the events in your life similarly determined by initial conditions set long ago? Or do you possess genuine agency, the ability to choose and change your path? This is the ancient question of free will, given cosmic context. I do not claim to have answers, but I find it fascinating that studying something as distant and exotic as the Great Attractor can lead us to questions as personal and profound as the nature of choice and destiny. Let me share with you some of the specific discoveries and observations that have enhanced our understanding of the Great Attractor over the decades since its discovery. In 1996, the Dwingaloo Obscured Galaxies Survey used radio telescopes to peer through the zone of avoidance, cataloging hundreds of previously unknown galaxies hidden behind the Milky Way's disk. This survey revealed the full extent of the Norma cluster and confirmed that a massive concentration of galaxies existed in the direction of the Great Attractor. In the early 2000s, the 2-micron all-sky survey, or 2MASS, mapped the entire sky in infrared light, which can penetrate dust much more effectively than visible light. This survey extended our view through the zone of avoidance, revealing the three-dimensional structure of galaxy distributions in that region. The data showed that the Great Attractor region is part of a larger wall of galaxies, a planar structure extending across hundreds of millions of light-years. More recently, in 2013, a team led by R. Brent Tully published a new map of galactic motions that defined the Laniakea supercluster. By analyzing the velocities of galaxies in 3 dimensions, they created a map showing the basins of attraction, the regions of space where galaxies flow toward common centers. Laniakea emerged from this analysis as a coherent structure with the Great Attractor region marking a significant, though not central, concentration point within it. These observations required painstaking work, measuring the distances and velocities of thousands of galaxies. Distance measurement in astronomy is notoriously difficult. For nearby stars, we can use parallax, the apparent shift in position as Earth orbits the Sun. But for galaxies millions of light-years away, parallax is useless. Instead, astronomers use a cosmic distance ladder, a series of methods that build upon each other, each calibrated by the previous step. Standard candles, objects with known intrinsic brightness, allow distance estimation by comparing how bright they appear to how bright they should be. The dimmer they appear, the farther away they must be. One crucial type of standard candle is a type Ia supernova, the explosion of a white dwarf star that has accreted matter from a companion star until it exceeds a critical mass limit. These explosions have remarkably consistent peak brightness, making them excellent distance indicators. By observing Type Ia supernovae in distant galaxies, astronomers can measure how far away those galaxies are. Combine distance measurements with velocity measurements, obtained by examining the redshift or blue shift of galaxy light, and you can map the three-dimensional structure and motion of the cosmic web. This is the work of decades, the collaborative effort of thousands of astronomers, engineers, and scientists building telescopes, developing instruments, collecting data, and analyzing results. The map of cosmic structure we have today represents one of humanity's great intellectual achievements, a comprehensive picture of our cosmic neighborhood out to distances of billions of light years. But even with all this progress, mysteries remain. One of the most intriguing concerns the precise nature of dark matter. We know it exists. Its gravitational effects are undeniable. The motions of galaxies in clusters, the bending of light by gravitational lensing, the formation of large-scale structure, all require far more mass than we can see. Dark matter provides that mass. But what is it made of? The leading candidate is some form of weakly interacting massive particle, or WIMP, a subatomic particle that has mass but interacts with ordinary matter only through gravity and possibly the weak nuclear force. Physicists have built sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to detect the rare occasions when a dark matter particle might collide with an atomic nucleus. So far, these experiments have not produced a confirmed detection, constraining the properties dark matter can have but not yet identifying it definitively. Alternative theories propose that dark matter is composed of axions, hypothetical particles much lighter than WIMPs, or primordial black holes formed in the early universe rather than from stellar collapse. Some scientists even question whether dark matter exists at all, suggesting instead that our theory of gravity needs modification. Modified Newtonian dynamics, or MOND, proposes that gravity behaves differently than we think on the largest scales, producing the effects we attribute to dark matter without requiring any invisible mass. However, most evidence favors the existence of actual dark matter particles over modified gravity. Observations like the Bullet cluster, where two galaxy clusters have collided and the distribution of mass inferred from gravitational lensing is separated from the distribution of visible matter, are difficult to explain without invoking dark matter. The formation of structure in the early universe, as revealed by observations of the cosmic microwave background, also requires dark matter. MOND struggles to explain these observations. The Great Attractor, with its vast concentrations of dark matter, represents both a challenge and an opportunity for understanding this mysterious substance. If we can precisely measure the distribution and behavior of dark matter in structures like the Great Attractor, we can test our theories and perhaps gain insights into its true nature. Future observatories, with better resolution and sensitivity, may allow us to map dark matter distributions in unprecedented detail, bringing us closer to solving this profound mystery. Another question that haunts the study of cosmic structure concerns the nature of cosmic voids. These enormous empty regions are not voids in an absolute sense. They contain some matter, just far less than average. But why did they become so empty? What are the dynamics within a void? Do small structures still form there, or does the low density prevent significant gravitational collapse? Recent observations suggest that voids may be even more interesting than previously thought. Some galaxies do exist within voids, and they appear to be different from galaxies in denser environments. They tend to be smaller, bluer, and more actively forming stars. This makes sense. Without frequent interactions and mergers with other galaxies, void galaxies evolve in relative isolation, steadily forming stars without the disruptions that larger galaxies experience. Voids also expand faster than the average cosmic expansion rate. As matter flows out of voids toward denser regions like the Great Attractor, the voids grow larger and emptier. This creates a feedback effect. As voids expand, the density contrast between voids and filaments increases, making structure more pronounced. Over cosmic time, the universe becomes more clumpy, with matter concentrating in filaments and clusters while voids expand. Understanding voids is crucial for a complete picture of cosmic structure. The universe is defined as much by its empty spaces as by its concentrations of matter. The great attractor exists because voids exist. Matter flowing out of voids must go somewhere, and it accumulates in structures like the great attractor. They are two sides of the same coin, both products of gravitational instability amplifying small initial fluctuations. Now, let us turn to a question that may have occurred to you. Are there other structures like the great attractor elsewhere in the universe? The answer is absolutely yes. The great attractor is just one of many massive concentrations of galaxies scattered throughout the cosmos. Some are even larger. The Shapley supercluster, which we have already discussed, is one example. Another is the Coma cluster, a rich cluster of galaxies about 320 million light-years away containing thousands of galaxies. There is also the Sloan Great Wall, a vast filament of galaxies discovered in 2003 stretching across approximately 1.3 billion light-years. It is one of the largest structures ever observed, a mind-boggling expanse of galaxies arranged in a coherent formation. Even larger is the Hercules Corona Borealis Great Wall, possibly extending across 10 billion light-years, though its existence as a single coherent structure is debated. These structures reveal that the universe is far from uniform. On small scales, up to hundreds of millions of light-years, structure is pronounced, with filaments, clusters, and voids creating a rich cosmic web. On the very largest scales, beyond a few billion light-years, the universe does appear to become more uniform, consistent with a cosmological principle that suggests the universe is homogeneous and isotropic when viewed on sufficiently large scales. But the existence of structures as large as the Hercules Corona Borealis Great Wall challenges this assumption. If such enormous structures exist, at what scale does the universe truly become uniform? Or is there no scale of uniformity, with structure all the way up? These questions remain open, and studying structures like the Great Attractor provides essential data for addressing them. Each of these massive structures has its own gravitational influence, creating its own attractor effect on surrounding galaxies. If you could map all the gravitational flows in the universe, you would see a complex pattern of streams and currents, with galaxies flowing along filaments, clustering in nodes, all while being carried along by cosmic expansion. It would resemble a turbulent fluid, with eddies and currents on every scale, except this fluid is made of galaxies rather than molecules, and it flows through expanding space rather than a fixed container. Let me now address one of the most provocative ideas in modern cosmology, one that relates to the great attractor and our motion through space. Some physicists have proposed that our universe might not be alone, that it might be part of a multiverse, a vast ensemble of universes each with potentially different physical laws and properties. In some multiverse models, these other universes could interact gravitationally with ours, creating effects that might be observable. Could the great attractor or the dark flow phenomenon be evidence of such interactions? Could we be seeing the gravitational influence of another universe? This is highly speculative, and I must emphasize that there is no confirmed evidence for such a scenario. The mainstream explanation for the great attractor involves only ordinary and dark matter within our own universe, concentrated in vast structures through billions of years of gravitational evolution. However, science advances by considering all possibilities, even exotic ones. If evidence emerged that could not be explained by known structures within our universe, if the dark flow were confirmed and could not be accounted for by any distribution of matter consistent with other observations, then more exotic explanations would need to be considered. For now, the multiverse remains a theoretical possibility rather than an observed fact, and using it to explain observations like the great attractor is premature. But the multiverse discussion highlights an important aspect of how science operates. We formulate theories based on observations and use those theories to make predictions. When new observations agree with predictions, our confidence in the theory increases. When observations disagree, we must either refine the theory or develop new ones. Occasionally, observations are so unexpected that they require revolutionary new thinking, overthrowing old paradigms entirely. The great attractor itself was such a surprise when first discovered, challenging astronomers' assumptions about galactic motion. Let us return to something more concrete. What future observations might teach us about the Great Attractor and cosmic structure? Several new telescopes and observatories are planned or under construction that will revolutionize our view of the universe. The James Webb Space Telescope, launched in late 2021, can observe in infrared wavelengths, allowing it to peer through dust and see distant galaxies with unprecedented clarity. While its primary mission focuses on very distant galaxies and the early universe, it may also contribute to mapping structures like the Great Attractor. Ground-based telescopes are also advancing. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will repeatedly scan the entire visible sky every few nights, creating an enormous database of cosmic objects and how they change over time. This will allow precise measurements of galaxy positions and motions, refining our maps of cosmic structure and flow patterns. Radio astronomy continues to advance as well. The Square Kilometre Array, an international project building the world's largest radio telescope, will be able to detect faint radio signals from billions of light-years away. Radio observations can penetrate the zone of avoidance, revealing structures hidden from optical telescopes. SKA will map the distribution of neutral hydrogen gas throughout the universe, tracing out the cosmic web in exquisite detail and allowing us to weigh the structures within it. In the more distant future, space-based gravitational wave observatories might detect the subtle warping of spacetime caused by supermassive black holes merging in galaxy collisions. As galaxies in the Great Attractor region interact and merge, their central black holes will eventually spiral together and merge, releasing enormous amounts of energy in gravitational waves. Detecting and studying these events would provide new insights into how structures form and evolve. What would you ask if you could speak to a scientist studying the Great Attractor? What questions burn in your mind when you contemplate our galaxy's motion through space? Perhaps you wonder whether we will ever truly understand dark matter and dark energy, whether the equations and theories we write down truly describe reality or are merely approximations. Perhaps you wonder whether life exists in the galaxies toward which we are falling, whether other civilizations are asking the same questions about their motion through space. The question of life elsewhere in the universe is one that fascinates both scientists and the public. The sheer number of galaxies and structures like the Great Attractor suggests that planets must be abundant. Our own galaxy contains hundreds of billions of stars, and we now know that planets are common around those stars. In the Great Attractor region, with thousands of galaxies, there must be trillions upon trillions of planets. It seems almost impossible that Earth is the only one to harbor life. Yet we have not detected any signals, any evidence of technological civilizations elsewhere in the cosmos. This is the Fermi paradox. If life is common, where is everyone? Many solutions have been proposed. Perhaps life is common, but technological civilization is rare, with most life never advancing beyond simple organisms. Perhaps civilizations destroy themselves soon after developing technology. Perhaps they are out there but choose not to communicate, or perhaps the galaxy is so vast that signals from other civilizations have not yet reached us. The Great Attractor adds another layer to this discussion. If civilizations exist in the galaxies flowing toward the Great Attractor, they too are experiencing this cosmic motion. Do they know about it? Have they mapped their place in the cosmic web as we are doing? Or are they still at an earlier stage of understanding, perhaps not yet aware that their galaxy is moving through space at all? Civilizations at different stages of development would have very different perspectives on cosmic structure. Imagine for a moment that we received a signal from an intelligent civilization in a galaxy within the Great Attractor region. The signal would have been sent more than 200 million years ago, traveling at the speed of light across the vast gulf between us. That civilization might no longer exist by the time we receive their message. Or they might have advanced to heights we cannot imagine, their technology and understanding so far beyond ours that their signal is incomprehensible to us. Any response we send would take another 200 million years to reach them. This is the challenge of cosmic communication. The distances are so vast and light so slow, relatively speaking, that real-time conversation is impossible. But perhaps that is not the point. Perhaps the very act of sending and receiving messages across such distances is meaningful, a demonstration that intelligence and curiosity can bridge even cosmic gulfs. A civilization that builds radio telescopes and listens to the cosmos is making a statement about values, about the importance of knowledge and connection. In receiving their signal, we would learn that we are not alone, that others share our desire to understand and communicate. That knowledge alone would be profound. Let me share with you one more fascinating aspect of the Great Attractor and cosmic structure: the role of computer simulations in understanding them. The universe is too large and evolves too slowly for us to conduct experiments. We cannot create a galaxy cluster in a laboratory and watch it evolve. Instead, astronomers use powerful computers to simulate cosmic evolution. These simulations start with initial conditions representing the universe shortly after the Big Bang, with small density fluctuations distributed according to what we observe in the cosmic microwave background. They then calculate how gravity causes these fluctuations to grow over billions of years, with denser regions collapsing and less dense regions emptying out. Dark matter and ordinary matter are both included, along with the effects of cosmic expansion and dark energy. Running such simulations requires immense computational power. Following the gravitational interactions of billions of particles as they evolve over cosmic time demands supercomputers performing quadrillions of calculations. But the results are spectacular. These simulations produce cosmic webs that look remarkably similar to what we observe in the real universe, with filaments, clusters, and voids all emerging naturally from gravity acting on small initial fluctuations. By comparing simulations to observations, scientists can test whether our cosmological model is correct. If simulations predict structures that do not exist in the real universe, or fail to predict structures that do exist, that suggests our model needs refinement. The fact that simulations reproduce the cosmic web so well, including structures like the Great Attractor, is strong evidence that we understand the basic physics of structure formation, even if mysteries remain about dark matter and dark energy. These simulations also allow scientists to explore counterfactual questions. What would the universe look like if dark energy were stronger or weaker? What if dark matter did not exist? What if the initial fluctuations were larger or smaller? By varying parameters and seeing how the simulated universe changes, researchers can understand which aspects of cosmic structure are robust and which are sensitive to specific conditions. This helps identify what observations would most effectively constrain our theories. In a sense, these simulations are experiments, just not physical ones. They are thought experiments made concrete through computation, allowing us to explore possibilities and test hypotheses in ways that would be impossible otherwise. They represent a new way of doing science, complementing observation and theory with computational exploration. Now, as we approach the conclusion of our journey through the cosmos, let me ask you to reflect on what the Great Attractor means to you personally. Does it change how you think about your place in the universe? Does knowing that you are moving through space at over 1,000,000 miles per hour, caught in gravitational currents shaped by structures hundreds of millions of light years away, make you feel differently about your daily life? For some people, contemplating cosmic scales is humbling, even overwhelming. The universe is so vast, and we are so small. What we do seems insignificant against the backdrop of galaxies and superclusters. But I would offer a different perspective. Yes, we are small, but we are also remarkable. We are arrangements of atoms that have become conscious, that can ask questions about the universe and find answers. We are matter that has become aware of itself, capable of wonder and curiosity and understanding. The Great Attractor does not care about us. It is not conscious or purposeful. It is simply mass, concentrated by gravity, warping space-time according to the elegant equations of general relativity. But we care about it. We have studied it, mapped it, given it a name. We have placed ourselves within the cosmic web and understood our motion through space. That is extraordinary. Moreover, the same physical laws that govern the Great Attractor also govern your body. Gravity, electromagnetism, the strong and weak nuclear forces, these are universal. The atoms in your body were forged in stars, scattered into space by supernova explosions, and incorporated into the cloud of gas that collapsed to form our solar system. You are literally made of stardust, your substance created in stellar furnaces billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created by nuclear fusion in stars or in the violent explosions that ended their lives. In this sense, you are intimately connected to the cosmos. You are not separate from the universe but a part of it, one of the ways the universe has become aware of itself. When you look up at the stars and wonder about the great attractor, you are the universe contemplating its own structure. That is both humbling and empowering. Throughout this exploration, we have encountered many unknowns, many questions without definitive answers. We do not know exactly what dark matter is. We do not know the precise nature of dark energy. We do not know whether the dark flow is real or an artifact. We do not know if life exists elsewhere in the universe. These unknowns might frustrate you, or they might excite you. I hope it is the latter. Science is not a collection of final answers, but an ongoing process of questioning and discovery. Every answer raises new questions. Every mystery solved reveals deeper mysteries. This is not a weakness, but a strength. It means there is always more to learn, always new frontiers to explore. The Great Attractor has been studied for nearly 4 decades, and we still do not understand everything about it. That is wonderful. It means future generations will have their own discoveries to make, their own contributions to our understanding. Consider the astronomers of the 22nd or 23rd century. Assuming humanity survives and continues to advance, what will they know about the Great Attractor that we do not? Perhaps they will have identified dark matter particles in laboratory experiments and mapped dark matter distributions throughout the Laniakea supercluster in exquisite detail. Perhaps they will have detected gravitational waves from merging black holes in Great Attractor galaxies, watching structure formation in real time. Perhaps they will have sent probes beyond our solar system, even beyond our galaxy, returning data from perspectives we cannot yet imagine. Or perhaps they will discover something completely unexpected, some phenomenon or structure that we in the 21st century cannot anticipate. The history of science is full of surprises, observations that nobody predicted but that revolutionized our understanding. Quasars, pulsars, gamma-ray bursts, dark energy, all were unexpected discoveries. What will be the next great surprise? The Great Attractor reminds us to remain humble in the face of cosmic complexity. The universe is under no obligation to make sense to us, to fit our preconceptions, or to be easily understood. We must approach it with openness and curiosity, willing to follow the evidence wherever it leads, even if it takes us to strange and unexpected places. As we reach the end of our journey, let us return to where we began, to you, sitting and listening, hurtling through space at over 1,000,000 miles per hour. You cannot feel this motion. There is no cosmic wind in your face, no sense of acceleration. You are in free fall, following a geodesic through curved space-time, and in free fall you feel weightless, motionless. The Great Attractor pulls, but you do not feel its grip. Yet it is there, implacable and immense, one of the great structures of our cosmic neighborhood. Billions of years from now, long after you and I and everyone we know has returned to dust, long after human civilization has either transcended to something we cannot imagine or vanished entirely, the Great Attractor will still be there, still pulling, still shaping the flow of galaxies through space. It was there billions of years before Earth formed, and it will be there billions of years after our sun dies. It is a monument to the power of gravity and the beauty of cosmic structure. So what should you take away from this exploration? Perhaps a sense of wonder at the universe we inhabit, so much larger and stranger than our ancestors ever imagined. Perhaps appreciation for the power of science and human curiosity to reveal hidden truths about reality. Perhaps a feeling of connection to the cosmos, a recognition that you are part of something vastly greater than yourself. And perhaps, most importantly, a question that will stay with you. a lingering curiosity that will bring you back to contemplating the night sky. What else is out there, beyond what we have discovered, waiting to be found? What other great attractors lurk in the depths of space? What other mysteries await our telescopes and our theories? The universe is vast and ancient and strange, full of wonders we have glimpsed and wonders we have not yet imagined. The Great Attractor is just one of them, one thread in the cosmic tapestry. By pulling on that thread, we have unraveled a larger story about structure and motion, about dark matter and cosmic evolution, about our place in the grand scheme of existence. Look up at the night sky tonight if you can. Find the constellation Triangulum Australe if you are in the southern hemisphere, or imagine it beyond the horizon if you are not. Know that in that direction, beyond the stars you can see, beyond the dust and gas of the Milky Way, lies the Great Attractor. It is invisible to your eyes, but real nonetheless, a concentration of thousands of galaxies, exerting its gravitational influence across hundreds of millions of light years. And know that you are moving toward it, right now, along with our Sun and all the stars of the Milky Way, flowing along currents in the cosmic web that have existed since the early universe. You are part of a journey that began billions of years ago and will continue for billions more. A voyage through space and time on a scale that dwarfs human history and human ambition. Yet here you are, aware of this journey, understanding it, placing yourself within it. That awareness is perhaps the greatest mystery of all. How matter organized itself into form capable of comprehending the universe that created it. You are stardust that can contemplate stars, atoms that can ponder the Great Attractor. And in that contemplation, in that wondering and questioning and seeking to understand, you fulfill something profound, something that justifies the entire cosmic journey that brought you into existence. You are the universe awakening to itself, looking back across billions of light years and billions of years of time, seeing its own grandeur reflected in thought and understanding. The Great Attractor is out there, dragging our galaxy through space. But you are in here, aware and alive and curious. And perhaps that, in the end, is the greater miracle.